The night sky has structures in it. They hold 1,000,000 galaxies. Modern astronomy broke our old maps. It showed us giants. They're so big, we have to rewrite every textbook. If our solar system was a grain of sand, some of these things would be the size of continents. This video looks at 25 cosmic structures. They're so large, they changed how we see our place. You'll get a new understanding of the universe's true architecture, from huge walls of galaxies to voids, staggering emptiness. Why does the cosmos organize itself on these scales? And what do these shapes say about the universe's final fate? What do you think of when you hear the word infinity? William Herschel, back in the 18th century, he was out there charting stars at night. He believed the Milky Way, that glowing band, was everything, the whole cosmos, a single island of light in an empty sea. That idea held for more than a century. It was a comforting thought. Then, in the 1920s, Edwin Hubble used the telescope on Mount Wilson. He saw something. It shattered that island idea completely. Those faint spirals in the sky, they weren't just gas clouds in our galaxy. They were other galaxies, entire cities of stars far away, so our Milky Way wasn't alone. It was just one of billions. That was the first big shift in perspective, but it was only the start. Galaxies became the new basic units, like individual stars in a much larger story. And astronomers started asking a new question. If galaxies are like stars, do they gather into clusters? And do those clusters form even larger patterns? The answer over decades was yes. Every time we built a tool to see farther, we found a new layer, a new, larger structure. Cosmologist J. Richard Gott talks about this as a series of perspective shifts. Each discovery makes the old frame of reference seem small, like realizing your hometown is just a neighborhood on a continent. The tools for this new vision are modern marvels. Massive redshift surveys like the Sloan Digital Sky Survey, they use light from millions of galaxies. They measure how much that light is stretched toward red. That tells them the galaxy's distance. It's like listening to a symphony where every note is slightly out of tune. And from that distortion, you can map the whole concert hall in 3 dimensions. Satellites peer into space, free of Earth's blurring atmosphere. Supercomputers stitch millions of data points together into one map of the observable universe. To navigate these maps, we need new units. A light year is the distance light travels in a year, about 6 trillion miles. It's a number that slips from your grasp. But for the cosmos, we use megaparsecs. 1 megaparsec is over 3 million light years. That's the scale where the universe shows its true architecture. This brings us to a foundational idea, the cosmological principle. It's the assumption that if you zoom out far enough, the universe should look roughly the same everywhere. A smooth, homogeneous soup of galaxies. It's a sensible starting point, but what if the map, when we finally built it, wasn't smooth at all? Take our own local neighborhood. The local group, it has our Milky Way, the Andromeda Galaxy, about 50 other smaller galaxies, all bound by gravity. On the cosmic map, it's a tiny, quiet village. The structures we're about to explore aren't villages. They're sprawling superclusters, immense walls and filaments. They make our local group look like a single house on a vast continent. Their very existence asks a profound question. What if the universe is fundamentally lumpy, textured with giants on scales we're only starting to comprehend? To find the answer, we have to meet the first of these giants, the closest one, the structure that began this whole era of redefinition. We had this idea for a long time about where we lived in the universe. We called it the Virgo Supercluster, a collection of galaxy groups all centered on the Virgo cluster, but that idea was wrong, or it was incomplete. It was just a part of something much, much bigger, Our real home is called Laniakea. The name is Hawaiian. It means immeasurable heaven, and it fits. This was the first time we could see one of these true cosmic structures. It changed our address completely. To find it, an astronomer named R. Brent Tully led a team. They did something different. They didn't just map where galaxies are. They mapped how they move, how they flow. It's like throwing leaves into a river. The leaves don't just drift, they're carried. They all go with the current toward a common point. Galaxies are like that. Gravity is the current, so this team tracked the motions. The subtle drifts of over 8,000 galaxies, and they mapped a cosmic watershed, a gravitational basin. They saw that all the galaxies in our region, our Milky Way included, are all streaming together, flowing in the same direction toward the same place. That entire territory, that basin of influence, is Laniakea. It stretches 520 million light-years across. It holds about 100,000 galaxies, and the Virgo supercluster we knew, it's just one part of it, one dense lobe, a suburb of this vast metropolis. At the center of Laniakea, there's a mystery. They call it the Great Attractor. It's not one object, it's a gravitational focal point, centered on the Coma Cluster, which is just a huge knot of galaxies. Everything in Laniakea over cosmic time is being pulled toward that region. Our Milky Way is out on a distant filament, a far arm of this web. You can picture a spider web. A huge one covered in morning dew. Each dewdrop is a cluster of galaxies. Our sun is on one tiny droplet, way out on a single strand, and the whole web, its dense center, is pulling everything inward. Gently, that's where we are, inside Laniakea. So that's our local supercluster, our immeasurable heaven. A structure so big we needed a new way of looking just to see we were inside it. And that makes you think, if this web with its 100,000 galaxies is just our local neighborhood, then what's the rest of the continent like? What holds Laniakea? Laniakea isn't an island, it's part of something bigger. Back in the 80s, astronomers were mapping galaxies, plotting them in 3 dimensions. They were like cartographers drawing coastlines without seeing the continent. And 2 scientists, Margaret Geller and John Huckra, they saw a pattern in their data. The universe wasn't just a random scatter of galaxies. It looked like bubbles or a sponge, huge empty regions surrounded by thin walls of galaxies. Their work started connecting dots across huge distances, and one of the first big patterns they saw was the Pisces-Cetus supercluster complex, which isn't a single bound object like a cluster. It's more like a mountain range, a trending alignment of mass, a filament stretching for about 1 billion light-years. It links several major structures, the Pisces, Cetus, and Pegasus superclusters, into one network. Our own Laniakea supercluster sits on its outer fringe. This complex was a revelation. It showed that superclusters could link into even larger architectures. These are the threads of the cosmic web. They trace the skeleton of the universe where dark matter and gas have funneled together over billions of years, pulling galaxies into these chains. The discovery challenged the idea of isolated structures. It proved the universe's large-scale structure is filamentary. These great walls of galaxies form the boundaries between even larger, emptier voids. So if the Pisces-Cetus complex is a mountain range, what's beyond it? The answer would come from a map so large, it revealed a structure that seemed to break the rules of cosmology. The Harvard-Smithsonian map was meant to show a smooth universe. In 1989, Margaret Geller and John Huckra showed a slice of the cosmos from the CF, a redshift survey. They plotted the data and it looked like a simple diagram. It became the stickman, and through the center of it there was this thick, dense line, a wall. The CF, a 2 Great Wall, not a solid thing, a statistical reality, a vast, flattened concentration of galaxies, over 500 million light-years long. At the time, it was the largest known structure. The scale was shocking. It went directly against the cosmological principle, that idea of a smooth universe. Robert Kirshner saw that map and said the universe was lumpy on scales no one expected. The cosmos had texture, it had architecture. Think of the early explorers. They thought the oceans were mostly empty. Then a survey finds a single, continuous coral reef, spanning an entire ocean basin, full of life, while the waters around it are barren. That was the impact of the Great Wall, a reef of galaxies. Its location helped define our local geometry. It sits toward Coma Berenices and Hercules. And right next to it, in contrast, is the Boötes Void, a region of staggering emptiness, hundreds of millions of light years across. The wall and the void, two sides of the same coin. They showed the universe has a foam-like topology, a cosmic sponge, matter in immense sheets and filaments, leaving behind vast, dark bubbles. This wall wasn't held together by gravity, not like a cluster. Galaxies at one end aren't bound to the other. It's a density fluctuation, a ripple from the early universe grown to an impossible size by expansion. Seeing it forced a question. If a survey of a small slice of sky could find something this enormous, what did that mean for the whole? The 1989 Great Wall was a benchmark. It redefined what large meant, but it was just a preview. The next surveys would look deeper, and they'd find something that made the Great Wall look like a neighborhood street. The CF, a Great Wall, held the record for more than 10 years. Then in 2003, a new map came out. It changed everything. The Sloan Digital Sky Survey. This was an automated telescope scanning the sky, collecting light from millions of galaxies. It built a 3D atlas of the nearby universe, deeper than anything before, more detailed, and in that data, astronomers found a filament, a structure of such staggering scale it seemed to defy expectation. They called it the Sloan Great Wall. It wasn't a single, solid barrier. It was a complex, a vast chain of superclusters linked together like beads on a string. At its heart were two immense knots of matter, superclusters designated SCL 126 and SCL 111, connected by fainter bridges of galaxies. The whole thing stretched for about 1.37 billion light years. To put that in human terms, if you could travel at light speed, a trip from one end to the other would take longer than the Earth has existed as a planet with complex life. It made the original Great Wall look like a local landmark. Cosmologist J. Richard Gott helped analyze it. He described the profound challenge it presented. The standard model of cosmology has a limit, a theoretical scale of homogeneity. Beyond that, the universe should start to look smooth. The Sloan Great Wall approached that limit. Statistical analysis suggested there was only about a 1 in 20 chance of finding such a structure in a universe that followed our models perfectly. Was this a rare but permissible fluke, a cosmic roll of the dice that came up spectacularly unlikely, or was it a hint that something in our understanding was incomplete? This wall became a crucial laboratory for studying dark matter distribution. The galaxies we see are just luminous tracers, streetlights outlining the shape of a much larger, unseen metropolis of dark matter. The sheer scale and density of the Sloan Great Wall implied an immense underlying scaffold of this mysterious substance. It forced theorists to run more sophisticated simulations, to see if their virtual universes could spontaneously grow something so colossal. The discovery sparked a debate, a healthy scientific debate that continues. Does the existence of such a giant point to exotic physics from the universe's first moments, a primordial seed that grew abnormally large, or is our observable universe simply one patch of a much grander cosmos? And within any given patch, rare giants can appear. The Sloan Great Wall stood as a monument to that tension, a beautiful, confounding structure. It redefined not just size but possibility. It proved that when we build a better map, the universe will show us something beyond our current imagination. And if this was the limit, then the next discovery would be truly incomprehensible. The Sloan Great Wall was already stretching what our models could handle. Then in 2013, a team using a different method announced something that didn't just stretch the limits, it seemed to break them. The Hercules-Corona Borealis Great Wall. If it's real, it's the largest arrangement of matter we've ever found. Its scale is so big it creates a kind of cosmological crisis. To find it, Istvan Horváth's team had to get clever. Mapping those faint, distant galaxies directly is so difficult, so they used cosmic lighthouses instead. Gamma-ray bursts, the most violent explosions we know, marking the death of massive stars, and massive stars form in galaxies. So a lot of gamma-ray bursts should mean a high density of galaxies and the mass that holds them together. By plotting hundreds of these brilliant flashes, they weren't just mapping light, they were mapping the underlying cosmic scaffolding, and the map showed a staggering concentration. A wall, the numbers are hard to grasp. This proposed structure spans an estimated 10 billion light-years. The observable universe is about 93 billion light-years across. So this one feature would cover roughly a tenth of the entire observable cosmos. It's not just an object in the universe, it's a fundamental texture of the universe on a scale we thought was reserved for smoothness. Horváth said it forces a question: is the universe truly the same in all directions on its largest scales? The cosmological principle of homogeneity hangs in the balance. Now the finding is hotly debated. Other researchers have looked at the same data and suggested it might be a statistical fluke, a chance alignment of bursts that aren't actually connected. It could be a projection effect, like several clouds at different distances lining up from our view to look like one giant, continuous cloud. The debate hinges on how we define a structure in the first place. When something approaches the size of the universe itself, do our usual definitions even hold? This wall, if real, is less a thing and more a region. A continent of mass. The implications are staggering for our theories of the universe's infancy. The standard model of cosmic inflation, that rapid expansion just after the Big Bang, should have smoothed out irregularities to a very high degree. Finding a lump this enormous suggests inflation worked differently, or the seeds for structure were planted in a way we don't yet understand. It's a mystery written across billions of light-years. And it forces us to look not just at the dense walls, but at what lies between them, because for every immense concentration of galaxies, there has to be a corresponding realm of nothingness. A void, but a wall of galaxies is only half of it, because for every concentration of light, there has to be a shadow, an emptiness. In 1981, astronomers Robert Kirshner, Augustus Oehmler, Paul Schechter, Stephen Schechtman, they were measuring galaxy redshifts, mapping things out, expecting it to be fairly even. And what they found was a hole in the sky so big it was hard to believe. The Boötes Void. Think of a sphere of space about 330 million light-years across. That distance light leaving one side when dinosaurs were here would just now be reaching the other side. In a volume that large, you'd expect tens of thousands of galaxies. Right ones, but surveys have only found about 60. It's a desert, a cosmic desert on a staggering scale. Robert Kirshner said it was like finding a giant bubble in the universe. A place where the universe just forgot to put galaxies. And it wasn't just an absence, it was a statement. The universe's structure isn't just defined by where matter is. It's defined by where it isn't. The cosmos has a topology like Swiss cheese or a sponge. Dense walls and filaments of galaxies are the cheese, and the voids are the holes. The Boötes Void showed that texture was real, and it was extreme, but a void isn't a perfect vacuum. It's an underdense region. The space is still filled with faint gas, the intergalactic medium, and it's threaded with dark matter filaments probably. But the gravitational pull, the one that normally pulls gas together to form galaxies here, it failed, or it was overcome. The main theory is these voids were carved out early, very early. Tiny regions that started with just a little less density than everything around them. Over billions of years with cosmic expansion, that small deficit snowballed. Matter flowed out toward the denser walls, draining the void like water from a bathtub. The void grew and it got emptier. The few galaxies inside the Boötes Void, they're fascinating. Loners, isolated island universes drifting in an ocean of nothing. Studying them is like studying life in the deepest deserts on Earth. How did they form here against the odds? Do they look different having evolved in such isolation? These lonely galaxies are natural laboratories. They show how environment dictates a galaxy's fate. To get the scale, picture a planet covered in dense, vibrant forests and luminous cities. Now picture a single desert on that planet. But this desert isn't a patch of sand. It's a continent of barren rock, larger than all the forests and cities put together. That's the relationship between the Great Walls and the Great Voids. The emptiness isn't the backdrop, it's the dominant feature. So what processes in the primordial universe could sculpt bubbles of nothingness that immense? The answer is in the seeds of all structure, planted in the first fraction of a second after the Big Bang. To understand the voids, you have to look back to the very beginning. To the faint whispers of sound that still echo through everything. The Boötes Void is profoundly empty, but it's far away, a distant curiosity. But what if the most important void wasn't out there, but right here? In a humbling twist, we might be living inside one. Our entire local group, the Laniakea Supercluster, our whole neighborhood, could be sitting in a vast, underdense bubble of space. That challenges a deep assumption in cosmology, the Cosmological Principle, the idea we don't occupy a special place. We've always assumed our region is average. What if it's not? This idea is called the KBC Void, named for the astronomers who proposed it in 2013, Ryan Keenan, Amy Barger, and Lennox Cowie. Their analysis of galaxy counts and distances suggested something startling. We might be near the center of a spherical region up to 2 billion light-years across that's emptier than the cosmic average, less packed with galaxies, less filled with matter. Our galaxy isn't on a dense wall, we might be in a valley. The evidence comes from a puzzle that's divided cosmology for years. It's called the Hubble tension. We have two main ways to measure how fast the universe is expanding, the Hubble constant. One method uses the ancient cosmic microwave background, the afterglow of the Big Bang. The other uses nearby objects like supernova and variable stars as distance markers. These two methods, checking the early universe and the modern universe, keep giving different answers. The local measurement says the expansion is faster. One compelling solution is that we are in a void. In an underdense region, gravity's pull is weaker. There's less mass holding space together, so the space inside the void expands a bit faster than denser regions outside. Our local measurements would naturally record this faster rate, while the cosmic microwave background gives us the true average rate for the whole universe. We are, in essence, living in a cosmic depression where the rules are slightly different. It's like measuring air pressure from inside a valley and assuming that's the pressure for the entire planet, not realizing the mountains around you have a different reading. Not all astronomers agree. Some larger galaxy surveys seem to show a more uniform distribution around us. The controversy is active. But if the KBC Void is real, it reshapes our cosmic address in a fundamental way. For decades, we mapped our place from the local group to Laniakea, thinking we were climbing a mountain of structure. We might instead be sitting in its basement. This isn't just a mapping error. It means our entire view of the universe's expansion, and even the nature of the dark energy driving it, could be subtly skewed by our unlucky location. We calibrate the cosmos from a point that may be profoundly atypical. It forces a shift. We look out at the great walls and filaments, those immense concentrations of galaxies, and we see them as the universe's grand features. But from their perspective, looking back, they might see us and our entire supercluster as a notable patch of emptiness, a local hole. This realization ties back to the cosmic web. It confirms that the sponge-like structure of voids and filaments isn't just a pattern out there. It is the pattern, and we are woven into it, perhaps residing in one of its hollow threads. And if our local void is real, it raises the question, what shapes these bubbles of nothingness in the first place? The answer lies in the faintest echoes from the beginning of everything. The universe isn't made of separate giants, it's all connected. The great walls, the voids, the superclusters, they form one single structure, the cosmic web. That's the ultimate architecture. We saw it when we could finally zoom all the way out. Modern simulations show it, like the Millennium Run, a universe-spanning network of dark matter filaments. They glow like strands in a three-dimensional spiderweb, or like a neural network, but cosmic in scale. This web changed cosmology. Our view shifted. From isolated islands to one interconnected structure, a living anatomy shaped by gravity over nearly 14 billion years, cosmologist Carlos Frenk described that moment. When sophisticated simulations finally matched our telescopic observations, it gave us a recipe for the universe. Here's how that recipe works. After the Big Bang, there was a period of hyper-fast expansion. Inflation, it planted tiny quantum seeds of unevenness, minuscule regions that were slightly denser. Over cosmic time, gravity acted on those seeds. The invisible scaffolding of dark matter began to clump first. Dark matter feels gravity but not light. It drew together into an immense, invisible network, strands and knots. Ordinary matter, the gas for stars and galaxies, was then funneled along that pre-existing highway. Galaxies condensed like dew on spider silk, along the densest filaments. Enormous clusters formed where filaments crossed, at the nodes of the web, and the vast spaces in between, drained of matter, became the great voids. You can picture the process like watching cream swirl into black coffee. The initial pour creates ripples and tendrils. They stretch, fold, and merge into complex, ever-changing patterns. The cosmic web is that pattern, frozen in space but dynamic across time. Gravity continuously pulls more material onto the filaments and into the nodes. This web dictates everything about a galaxy's life, its fate, its motion, its shape. A galaxy born on a dense filament will be pulled toward a cluster, possibly merging with others along the way. A galaxy born in a void may live a solitary, quiet existence. Our own Milky Way resides on a relatively quiet strand. Part of the local sheet, part of the Laniakea Supercluster, flowing gently toward the great Attractor node. To understand the power of this structure, you look to where the web's threads pull tightest. The dense, violent, brilliant intersections where the universe concentrates its might. The cosmic web has these nodes. Some are much more massive than others. Back in the 1930s, Harlow Shapley was mapping galaxies. He saw this extraordinary concentration toward Centaurus, a dense patch of sky glowing with thousands of galaxies. At the time, he couldn't grasp the scale. Decades later, with redshift surveys, we understood. It wasn't just a cluster. It was the heart of the largest mass accumulation in our local universe. The Shapley Supercluster, about 650 million light-years away, a gravitational titan, a supercluster complex, a dense knot where several immense filaments of the cosmic web intersect. Surveys mapped its influence, the 2-degree field survey. This region holds dozens of massive galaxy clusters, each one a city of thousands of galaxies. The core has clusters like a 3558, a behemoth. Galaxies swarm there in a frenzied gravitational dance. The mass concentration is so immense, its gravity reaches across cosmic distances. It's a major contributor to the Great Attractor phenomenon, maybe the dominant one. Remember our flow within Laniakea, our local group, and every galaxy for hundreds of millions of light years around us is being pulled. A significant part of that pull comes from Shapley. It helps solve the mystery of our galaxy's peculiar velocity, that extra motion on top of the universe's expansion. We are falling toward this distant mountain range of galaxies. Picture a planet with a single, colossal mountain range, so massive its gravity tugs on tectonic plates thousands of miles away. That's Shapley's influence. It isn't a single, bound object. Galaxies at its far edges aren't tied to the core. It's a statistical reality, a region where the universe piled matter into a staggering overdensity. Its discovery confirmed the nodes aren't created equal. Some are gentle hills, others are Everest-sized peaks that shape the flow of the cosmos. If Shapley is one of the most massive knots we know, it forces a new question. What if entire superclusters link together into formations that make Shapley seem like just a component? The Shapley Supercluster is a dense knot, a kind of mountain in the cosmic web. But not all structures are knots. Some are the threads, the filaments. In the southern sky, there's a spectacular example, a river of galaxies, so long it defies our sense of scale. That's the Horologium-Reticulum Supercluster. Its discovery came from mapping the southern skies, patient work, surveys like the 2-degree field and the 6-degree field. They revealed a chain, a line of bright galaxy clusters like pearls on an invisible string. Even in two-dimensional maps, this filament stood out, a stark, linear feature near the south galactic pole. In 3 dimensions, its true nature emerged. It's not a compact sphere. It's an elongated filament, a classic pore supercluster, lower density than a knot like Shapley. But it makes up for that in length. It stretches for over 550 million light-years, a distance so vast, light from one end began its journey before complex life existed on Earth. Astronomers see structures like this as cosmic channels. They guide the motion of matter, funneling galaxies along gravitational highways toward the denser nodes. The Horologium-Reticulum filament is precisely that, a river in space. Its banks are defined by several massive Abell clusters, with fainter galaxy groups and strings connecting them. It lies about 900 million light-years from us, and it runs right alongside one of the largest voids we know, the Horologium Void. That's no accident. It shows the fundamental relationship in the cosmic web. The immense filaments form the boundaries of the even more immense bubbles of emptiness. Matter drains from the void centers. It piles up along these walls and threads. You can picture a great terrestrial river system, like the Amazon. The main channel is the dense core of the filament. The tributaries are the fainter galaxy groups feeding into it, and the massive galaxy clusters are like great cities. They grew at the confluences where the gravitational trade routes meet. This supercluster isn't an isolated river. It's part of a continental watershed. Studies suggest it's likely connected, through fainter filaments, to the immense Shapley concentration far away. It's one thread in a tapestry spanning billions of light-years. So what keeps such an elongated structure coherent? The galaxies at one end aren't gravitationally bound to those at the other. Instead, they share a common origin. They all condensed from the same primordial overdensity, a slight ripple in the early universe that stretched into a filament as space expanded. They're flowing together along the same dark matter trough, like water droplets finding the path of least resistance down a mountainside. This river of galaxies shows the universe's structure isn't just about concentrated power. It's also about extended connection, but when these rivers and threads weave together, they don't just form knots, they can create entire continents. Immense flat sheets of galaxies, that's the next order of magnitude in cosmic architecture. The southern sky had a secret. For decades, the best maps of the cosmic web came from telescopes in the north. But then there was a big survey using the Anglo-Australian telescope in New South Wales, the 2-degree field galaxy redshift survey. It mapped hundreds of thousands of galaxies below the dusty plain of the Milky Way. And it found something, a southern version of the Great Northern Walls, the Sculptor Wall, a huge sheet-like structure, a kind of backbone in our local universe. It stretches about 500 million light-years. It's not a solid wall, it's a dense filament, a ridge in the cosmic landscape, maybe 80 million light-years thick. This wall connects things. It links the big Sculptor and Fornax galaxy clusters into something larger, the Pisces-Cetus Supercluster complex. It completes the local map. So now we see our cosmic neighborhood is framed by these immense structures, one in the north, one in the south. The famous Sculptor group with the Sculptor galaxy, that's just a local spur on this greater wall. A suburb on a continental shelf, the wall's orientation matters. It helps define the edge of a nearby emptiness, the local void. You can picture a vast continental shelf under an ocean. The Sculptor Wall is that shelf. Galaxies cling to its incline, and beyond it, the seafloor drops away into the profound dark of the void. The 2-degree fieldwork showed these walls aren't random. They're the fundamental sheets of the cosmic sponge. Finding this southern wall proved a point. The universe builds these structures in all directions. It's isotropic. There's no preferred up or down in the grand architecture. But if walls and filaments are the sheets and threads, what happens when they curve? When gravity weaves them into shapes that aren't just linear but closed, that leads to patterns of a different, almost impossible geometry. The cosmic web can produce more than walls and rivers. In 2015, a team of Hungarian and American astronomers found something that didn't fit the patterns. They were looking at gamma-ray bursts, those flashes from dying stars, and they saw a ring, a near-perfect circle on the sky, traced by 9 of these events. The Giant GRB Ring, its diameter is 5.6 billion light-years. It's not a physical ring of galaxies. It's a statistical pattern. The events are so far apart, light from one side would take over 5 billion years to reach the other. If it's a real 3-dimensional structure, its scale is beyond comprehension. It's far larger than any theoretical limit for a single gravitationally linked structure. So what could create that shape? The lead astronomer, Lajos Balazs, suggested it might be a fossil, a remnant from the universe's infancy called a baryon acoustic oscillation. In the first few 100,000 years, the universe was a hot, dense plasma. Sound waves rippled through it. When the universe cooled enough for atoms to form, those waves froze in place. They imprinted a preferred scale into the distribution of matter. We see that scale as a tendency for galaxies to be separated by about 500 million light-years. But the Giant GRB Ring is an order of magnitude larger. Could it be a single, enormous shell from one of those primordial sound waves seen in projection? A cosmic echo, frozen and expanded to a monstrous size. The odds of 9 such rare events aligning by pure chance are incredibly low. It's like looking at a map of a continent and seeing a perfect circle of the world's rarest, most powerful volcanoes, all erupting in a similar time frame. The pattern demands an explanation. Other scientists have offered alternatives. Maybe it's not a shell, but the edge on view of an immensely long, thin filament, a wall seen as a circle because it's oriented directly toward us. Or maybe it's a temporary alignment, a chance configuration that will dissolve as we map more gamma-ray bursts. But the ring's near-perfect circularity makes those explanations difficult to accept. It points toward something more fundamental, perhaps a texture in the fabric of space-time itself from the earliest moments, a defect that seeded structure on a scale we are only beginning to perceive. This single, mysterious ring challenges our understanding of how the universe organizes matter on its grandest scales. If such a perfect geometric shape can be etched into the cosmos, what other impossible patterns might be waiting, hidden in the faint afterglow of creation itself? The oldest light we can see carries a faint mark. Back in April of 2013, the Planck satellite from the European Space Agency gave us its map of the cosmic microwave background. That's the leftover glow from the Big Bang, a picture of the universe when it was only 380,000 years old. And the map is smooth, incredibly smooth, which tells us how uniform everything was back then. But it's not perfect. There's one place that doesn't fit. In the constellation Eridanus, there's an area that's much colder than the rest, the CMB cold spot. It's a patch of sky, maybe 5 times the size of a full moon, and it's about 70 microkelvins colder than the average. For cosmologists, that's a deep puzzle. Is it just a fluke, a random blip in the data, or is it a sign pointing to something huge and unseen sitting in front of us? The main idea, though it's debated, is that it's a shadow cast by the biggest void we've ever imagined, the Eridanus Supervoid. To see how a void could make a cold spot, there's a subtle piece of physics called the integrated Sachs-Wolf effect. Think of a photon, a particle of that ancient light, traveling for over 13 billion years to get here. For most of that trip, it moves through a universe where gravity and dark energy are in balance. But if that photon goes through a truly enormous region of space, a supervoid, things shift. When it enters this underdense valley, there's less gravitational pull holding it back. It actually gains a little energy going in. Then, billions of years later, as it comes out the other side, the universe is more dominated by dark energy. It has to climb out of a gravitational well that's actually gotten shallower. The total effect is the photon loses a bit of energy overall, and for a microwave photon, losing energy means shifting to a longer, colder wavelength. So a vast, nearly empty region of space acts like a cosmic hill. Light from the Big Bang, after crossing it, arrives here slightly colder. That's the theorized shadow of the Eridanus supervoid. The hunt for this void has been thorough. Astronomers have scanned that part of the sky, looking for the absence of galaxies. Some work suggests they found it, a proposed underdensity about 1.8 billion light-years across, with maybe 20% less matter than average. The scale is hard to grasp. It would be, by a huge margin, the largest void ever seen, but the evidence isn't solid yet. The void's signal in galaxy surveys is weak, and some analyses don't see it at all. The problem is huge. Confirming a structure that large means mapping galaxies across an immense volume of space, right at the edge of what our current surveys can do. The mystery gets stranger with other ideas. Some physicists, like Laura Mersini-Horton, have suggested the cold spot could be evidence of a collision with another universe in the multiverse, a kind of bruise from a primordial encounter. That idea grabs people, but the main focus is still on the supervoid. Whether it's a void or something weirder, the cold spot is a frontier. It raises a basic question about how big structures can get. Can voids grow to be almost 2 billion light-years across? If they can, their shadows might be written on that first light. It would prove these bubbles of nothing aren't just passive background. They're active, shaping what we see, able to leave a chill in the echo of the Big Bang. The cosmological principle makes a prediction. There has to be a scale, a distance where the universe finally gets smooth. That's the end of greatness. You zoom out far enough, and the walls, the filaments, the voids, they all blur into a uniform soup. Our models say this should happen at a few 100 million light-years. Beyond that, no single structure should dominate. This is a test. If we keep finding structures larger than that limit, our basic picture is wrong. In the textbooks like John Peacock's, they frame this with statistics. They use the two-point correlation function. It measures how galaxies cluster. It quantifies the lumpiness. The prediction is that this clustering signal fades to zero as you go to larger scales. The end of greatness is where that signal vanishes. It's a statistical horizon. The contrasts become too faint to matter. The universe should finally look homogeneous. But the discoveries tell a different story. The Hercules-Corona Borealis Great Wall, if it's real, is a 10 billion light-year challenge. It says the transition scale might be much, much larger. Or maybe we're seeing a statistical outlier, a cosmic roll of the dice. In an infinite universe, even wildly improbable things can happen somewhere. The question is whether we're looking at that one in a trillion place. To calibrate expectations, cosmology has a natural ruler, the Baryon acoustic oscillation. Those primordial sound waves frozen in space, they set a preferred scale. About 500 million light-years. It's the universe's fundamental note, a wavelength imprinted on the galaxy distribution. We see it as a slight tendency for galaxies to be separated by that distance. This BO scale is like the dominant wavelength of ocean waves. From a high-flying plane, the ocean looks smooth. From a ship, you see individual waves, crests, and troughs. The end of greatness asks if we've reached the altitude of that plane, or if we're still on the ship, seeing waves that are part of even larger swells. Finding walls and voids on scales of 1 billion light-years or more suggests we might still be on the ship. The ocean isn't smooth yet. The lumpiness might extend to scales that strain our models of the universe's infancy. To find the answer, we have to push our vision wider and deeper into time. We need to look at the most distant, ancient large structures. Do they obey the end of greatness? Or do they show giants being born in the cosmic dawn? The end of greatness is a prediction, but the universe tends to defy our predictions. To test it, you have to look across space and also back in time. In 2018, a team of astronomers used an instrument called VIMOS. It's on the Very Large Telescope in Chile. They pointed it at a patch of sky in the constellation Sextans. They weren't looking at the modern universe. They were looking back to when the cosmos was only about 2.3 billion years old, just a fraction of its current age. And in that ancient light, they found something that shouldn't have been there yet. A colossal, chaotic structure, a tangled web of gas and young galaxies caught in the middle of assembling itself. They named it Hyperion after the Titan. It's the largest and most massive proto-supercluster we've ever found from that early time. The lead researcher, Olga Cuciotti, described seeing the data. It was a surprise, finding a structure this big, this complex, so soon after the Big Bang. It challenges how we think gravity pulls the universe into shape. Hyperion's mass is staggering, over 1 million billion times the mass of our Sun, and it wasn't just a simple blob. Detailed mapping showed a complex architecture. At least 7 distinct high-density regions, already connected by faint filaments of young galaxies. This is the cosmic web in its infancy, a blueprint for a future Titan. Think of a modern metropolis like New York or Tokyo. Now imagine looking back in time and seeing that same land when it was just small settlements, dirt roads connecting them. The first foundational stones for future skyscrapers being laid. That's Hyperion, a metropolis under construction, seen the moment its foundational grid is being drawn. Its existence tells a story about the initial seeds of the universe. For gravity to sculpt something this large, this massive, in just 2 billion years, the initial overdensities had to be exceptionally pronounced in that region. Those tiny quantum ripples from inflation. It suggests the early universe wasn't a perfectly smooth canvas with tiny, uniform imperfections. It might have had some regions that were significantly more lumpy from the very start. Destined to become giants ahead of schedule, studying Hyperion is like finding the childhood home of a future world leader. The early environment already hints at the extraordinary path ahead. It forces cosmologists to refine their simulations, to allow for these rare, fast-growing behemoths in the adolescent cosmos. What does an early giant like this tell us about the initial conditions? The ones imprinted at the birth of everything. To understand that, you have to look beyond the distribution of galaxies to the largest possible patterns. The ones etched into the fabric of space-time itself. The name sounds like something from a cosmic thriller, the axis of evil. It's not a structure, it's a pattern. A possible flaw in the map of creation. Scientists had the most detailed map of the cosmic microwave background from the Planck satellite, a portrait of the infant universe. And they found something unsettling. The largest fluctuations, the hot and cold spots, they aren't random. They seem to align weakly but persistently. They align with the plane of our solar system and our galaxy's motion. That correlation defies a basic expectation. If the universe is isotropic, the same in all directions, these patterns shouldn't point anywhere. The chance alignment of these largest modes, the quadrupole and octupole moments, with our local geometry, it feels, to some, like a cosmic conspiracy. Cosmologist Kate Land, she co-authored an early paper on this. She captured the dilemma. She said it was hard to believe the universe was really aligned with us. But the signal was there, quietly challenging our assumptions. The implication is profound. A preferred direction in the cosmos would directly challenge the cosmological principle. That's the bedrock of modern cosmology, what Einstein relied on. It would suggest the universe has a spine, a subtle grain like wood. To visualize it, think of a perfectly round fruit. You cut it open, see the seeds scattered randomly, but then you notice with a chill that the largest seeds form a faint line, and that line matches the path of your own knife. Is the fruit's interior aware of your cut? The axis of evil asks a similar question. Is the universe's oldest light aware of our insignificant local frame? Most researchers lean toward more mundane explanations. It could be residual contamination, our own galaxy's dust not fully subtracted from the data. It might be an unlikely statistical fluke. In a universe of infinite possibilities, even a 1 in a million alignment might show up somewhere. Perhaps we are that somewhere. The debate is ongoing, a quiet tension at cosmology conferences, but if it isn't an artifact, the implications ripple outward. It could point to pre-inflationary relics. Textures in spacetime from before the Big Bang. Or, more speculatively, it might be a sign of something beyond our observable horizon. A gravitational tug from a structure so immense it warps the very background of our universe. This speculative frontier pushes us to consider constructs that aren't just large but foundational, patterns that might govern the cosmos itself. The axis of evil is one pattern in the light. But there's another pattern in the motion. Back in 2008, data came from the Wilkinson Microwave Anisotropy Probe. It shook things up. A team, led by Alexander Kashlinsky, was looking at hot gas in galaxy clusters, very distant ones. They used a subtle method, the kinetic Sunyaev-Zeldovich effect. It's like a fingerprint for a cluster's movement through the cosmic microwave background. And what they found was startling. Hundreds of clusters spread over billions of light years. They seemed to be streaming together in a coherent direction. A shared bulk flow, they called it the dark flow. This wasn't just the gentle drift of galaxies inside something like Laniakea. This was bigger, a current on a scale that seemed impossible. All these clusters were moving toward a point in the sky, in the constellations Centaurus and Hydra. The implication was deep. In the standard model, large-scale motion in the universe should be random. Smoothed out by expansion, the dark flow suggested a pull, a gravitational tug from something so massive, so distant, that its source had to be beyond our observable horizon. Think of leaves on a calm pond. If they all start drifting the same way, you don't think the leaves decided it. You look for the source of the current. A hidden spring, maybe, an underground stream feeding into the pond. The dark flow points to a cosmic spring, a source of gravity outside our map. Alexander Kashlinsky has defended this signal through later analyses. He says it's a real phenomenon, a fossil imprint from the epoch before cosmic inflation, or more speculatively, it could be the gravitational influence of a neighboring universe in a multiverse. A structure so vast it redefines what outside even means. This flow challenges the idea that dark energy's repulsive force is the only driver on the largest scales. It introduces a directional preference, a cosmic tilt our models don't predict. Naturally, a claim this bold faces scrutiny. Other teams, using data from the Planck satellite and different techniques, haven't found the signal. They suggest it could be an artifact, from imperfectly subtracting our own solar system's motion through the cosmic microwave background. Isolating a subtle drift across those distances is a huge technical challenge. Like trying to measure the ocean's deepest currents while bobbing in a small boat during a storm, the debate isn't settled. It's a quiet tension at the frontier. But the idea persists because of what it represents, a window into the truly unobservable. If the dark flow is real, it means our universe isn't an isolated bubble. It's being shaped by geography we can't see. These clusters are like buoys anchored in our visible cosmos, but their drift hints at the topography of a greater reality. Beyond the horizon, it pushes the inquiry to the limit, from patterns within our universe to the possibility of structures that contain it. The end of greatness might not be real. It could just be a limit of what we can see. There's another idea that's been around for a long time. It says the universe's structure doesn't smooth out. It just repeats. This is the fractal cosmos, a universe built in layers where clusters hold smaller clusters, and those hold even smaller ones, on and on forever. The astronomer Carl Charlier suggested this in the early 1900s. He pictured it like a Russian doll with no final, smooth shell. For a long time, that was just a thought. Then new galaxy surveys gave it new life. The physicist Luciano Pietranero became a major voice for it. He and his team looked at the data from big redshift surveys. Their finding was striking. They said the galaxy distribution shows clear fractal properties, and there's no sign it turns smooth, even at the farthest edges of what we can observe. In this view, the universe isn't becoming homogeneous. It's lumpy by its very nature, a web that never ends. To get a fractal, think of a coastline. From far away, it has one length. Zoom in and you see bays and peninsulas. That makes the measured length longer. Zoom in closer and you see the jagged edges of every single rock. The structure is self-similar. It looks about the same at different scales. Pietranero's analysis pointed to a fractal dimension around 2. That number is important. It means matter isn't arranged in solid three-dimensional balls. It's arranged in a complex sheet-like network, a cosmic web, and this web texture stays no matter what scale you look at. This directly challenges the foundation of our standard models. The Friedmann equations assume we can average matter into a smooth fluid on large scales. If the universe is fractal, there is no smooth average density. The equations we use for cosmic expansion and fate would need a complete rewrite. The debate here is intense. It goes to the heart of how we do science. The cosmological principle that the universe is uniform and the same in all directions isn't just an observation. It's a simplifying assumption. It makes the math of general relativity possible. It lets us model the whole universe. Without it, the task becomes incredibly complex. Supporters of the standard model point to the cosmic microwave background. Its remarkable uniformity, they say, is the ultimate evidence for smooth beginnings. Fractal advocates argue back. They say the CMB is a snapshot of a hot, dense plasma. It's not the distribution of galaxies that formed billions of years later, after gravity did its clumping work. They point to certain analyses of galaxy clustering. These seem to show correlations extending to the largest scales we've surveyed with no clear end. Think of the Mandelbrot set, that iconic image of infinite complexity. You zoom into any edge and you find the same swirling, intricate patterns repeating in endless variation. Is our universe like that? Are the great walls and voids we see just one level of a pattern that goes on forever, both inward and outward? This view is still controversial. It's not widely accepted, but its power is in the question it forces us to ask. It demands we prove smoothness, not assume it. It suggests our search for the largest structures might be a journey with no end, a descent into an infinite labyrinth of matter and empty space. And if the visible architecture is this complex, what about the invisible scaffolding holding it all up? That leads us to the true dark giants, structures defined not by the light they emit, but by the absolute absence of it. The galaxies we see, they're just the bright part. The tip of something much larger. There's this huge structure around us, around the Milky Way, Andromeda, the whole local group. It's made of something we can't see. A diffuse cloud, particles we don't know, a dark matter halo, that's the biggest thing we're part of, and it's invisible. Its gravity holds our galaxies together. It sets their orbits, decides their future. It'll bring them together eventually. A merger billions of years from now. Simulations have given it a shape. Projects like Via Lactea, Elvis, it's not a simple sphere, it's triaxial, lumpy in places, a relic of how it formed, probably 3 to 5 million light years across. Edges are fuzzy, it blends into the cosmic web. Think of the local group like a city at night from above. The streetlights are the galaxies, bright ones like ours, Andromeda. Smaller, fainter ones the dwarfs, but the city isn't just the lights, it's the land underneath, the hills, the valleys. The dark matter halo is that land. You don't see it, but you know it's there by how things move. The paths of cars, the motions of satellite galaxies, they show the terrain. We map it through motion. Dwarf galaxies around the Milky Way move too fast for just the stars to explain. Andromeda and the Milky Way are on a collision course because their gravity, mostly from this shared dark halo, beats the expansion of the universe. The mass is hard to grasp, over 100 times the mass of all the stars and gas in the local group combined. That invisible bulk makes us an island, bound in an expanding cosmos, and it's not isolated. It's a node, a thickening in a filament of the cosmic web. It grew over billions of years, fed by streams, smaller subhalos. Tributaries funneling into this well. Inside, thousands of smaller dark clumps are predicted to orbit. Some might hold faint dwarf galaxies, others are just dark. That raises a question. If our small local group sits in something this immense, how many of these are out there? Do they cluster to a dark counterpart to the cosmic web? The answer points to the largest assemblies of gravity, where even dark matter reaches its limit. The dark matter halo around our local group, it's just a local knot. A knot in this huge, invisible web. But where that web gets densest, where it really knots up, gravity makes something else, something bigger. These are galaxy clusters. The largest things in the universe that gravity holds together. And there's one, the Coma Cluster, that's a historic one. For a long time, it was just a fuzzy patch in the constellation Coma Berenices, but in the 1930s, it became something else. Fritz Zwicky was looking at it, studying how its galaxies moved, and he did a calculation. A shocking one. The mass you could see from the stars, it wasn't nearly enough. The galaxies were moving too fast. They should have flown apart, so he said there had to be something else. Some unseen matter, Dunkel Materie, providing that extra gravity. That was one of the first real arguments for what we now call dark matter. Now, the Coma Cluster is a textbook case. A rich cluster, over 1,000 galaxies, all held together. But to really see its scale, you need X-ray eyes. Telescopes like Chandra, they look into its heart. And they don't just see stars, they see this vast atmosphere, a halo of gas heated up to millions of degrees, that glowing plasma. It's a fossil record. It tells you how the cluster grew violently. Over billions of years, smaller groups of galaxies fell into Coma's gravity well. Their gas got ripped away, heated by the shock, and it all added to this seething reservoir. The amount of this hot gas, you can map it by its X-ray glow, and that lets you weigh the whole system. The numbers are staggering. The cluster spans about 20 million light-years. Its total mass is thousands of times the Milky Way's, but its influence goes further. This cluster is the dense, bright core of something bigger, the Coma Supercluster, part of the original Great Wall. Its gravitational domain, its halo, stretches out past the last visible galaxy. That creates a dramatic environment inside. For the galaxies trapped there, near the crowded center, something happens. Astronomers call it strangulation. A spiral galaxy comes in. It's rich with cold gas, ready to make new stars, but this is hostile territory. The intense pressure from the hot cluster gas, it acts like a cosmic wind. It strips the fuel away. Over time, the star formation stops. The galaxy changes from a vibrant blue spiral into a passive red elliptical. The cluster is like a giant whirlpool. In a cosmic ocean, smaller Eddie's galaxy groups, they get drawn toward it. Inexorably, they're torn apart, their identities lost, their material gets assimilated into the greater whole, that cannibalistic growth. That's how all massive clusters are built. The Coma Cluster shows us the end result in our local universe. It's an upper limit, in a way, the most massive, bound object we can easily study. But is it the ultimate limit? To answer that, you have to look further. Beyond our cosmic backyard, to the most extreme clusters, the most distant ones ever found. El Gordo, the fat one, that's what they called it. A galaxy cluster so massive, so far away, it felt like a kind of awe. Its real name is just letters and numbers, but that nickname stuck. They found it by its shadow, not by starlight. Astronomers were using the Atacama telescope and the Planck satellite, looking for these imprints on the cosmic background. A cold spot, a kind of shadow left by hot gas, and one of those shadows was enormous. Felipe Menanto, who led the team, said it was like finding a full-grown adult in a kindergarten. It wasn't supposed to be there, not that big, not that early. El Gordo is about 7 billion light-years away. We're seeing it when the universe was maybe half its current age. Its mass is hard to grasp, 3 quadrillion times the Sun. For gravity to pull that together in 7 billion years, it means the seeds had to be incredibly dense from the start. But then, it's not just one thing, it's a collision. Data from Chandra and Hubble showed that. It's 2 huge subclusters, each like the Coma Cluster, smashing into each other. Millions of miles an hour, not 2 galaxies merging, 2 entire metropolises of galaxies, thousands of them, set in this sea of gas. The energy is unimaginable. Shock waves heat the gas to hundreds of millions of degrees. It becomes a natural particle accelerator, far beyond anything we could build, and you can see the violence. There's a bullet of hot gas in the X-ray data, ripped away from one subcluster during the crash. That separation is the clue. The gas, being normal matter, slams into the other gas and slows down. But the galaxies and the dark matter halos around them, they don't interact. They're collisionless. They pass right through. So the mass, traced by gravitational lensing, isn't where the hot gas is. The mass has moved ahead, leaving the gas behind. That split between what we see and where the gravity is, that's direct evidence for dark matter. Its non-interacting nature playing out on this huge scale. And could there be something bigger? Maybe, but we might be looking right past it. Our view is blocked in one direction, by the plane of the Milky Way. The zone of avoidance, stars, gas, dust, hiding maybe a quarter of the sky. So it's possible. An even larger giant, a supercluster, could be sitting behind that veil. Its shadow just waiting, which means the search for the largest structures might have to turn back toward our own neighborhood, to whatever's hidden just out of sight. The Milky Way is a band of light, but it's also a wall, a dense disk of stars and gas and dust. It blocks our view of nearly a quarter of the distant universe. Astronomers call this the Zone of Avoidance. For a long time, it was a blank spot on our maps, a place of pure speculation, but from behind that wall, we could feel a pull. Our galaxy is drifting. Thousands of other galaxies are drifting too, all in a specific direction, like we're caught in a vast, invisible current. That was the mystery. The Great Attractor, in the late 70s and 80s, mapping galaxy motions showed something unsettling. Our local group, and a huge swath of space around it, isn't just expanding with the universe. It has an extra velocity, a peculiar motion. It's carrying us toward a point in the constellations Centaurus and Norma, a region that lies directly behind the Milky Way's brightest central bulge. The source of this pull was called the Great Attractor. It became a major puzzle. What colossal mass could be tugging on so many galaxies, and why couldn't we see it? The answer was in the Zone of Avoidance. Looking through our galaxy's dusty plane with optical telescopes is like trying to see distant mountains through thick fog. Astronomer Renée Cron-Courtoueg spent her career mapping this hidden frontier. She talked about the thrill of the hunt, using instruments sensitive to different kinds of light to penetrate the obscuration. One breakthrough came with radio telescopes, listening for the faint signature of neutral hydrogen gas, the fuel for stars, at a wavelength of 21 centimeters. This revealed galaxies completely hidden to optical surveys, like Dwinjaloo 1, a massive spiral galaxy lurking almost behind our own. Infrared surveys from space telescopes like Spitzer added another layer. Infrared light passes through dust more easily. It let astronomers census the stars in hidden galaxies. Piece by piece, the map behind the veil filled in. The Great Attractor, it turned out, wasn't a single monstrous object. It was a confluence of mass, a gravitational focal point, created by the combined pull of several immense structures. The dense Norma cluster sits near its heart, but the true source is the entire central density of the Laniakea Supercluster, that immeasurable heaven we call home. Our flow toward it is just the downhill slope of a cosmic watershed, but the story might not end there. Some measurements suggest the pull could be even stronger than Laniakea alone can explain. Could there be more mass, even larger structures, still hidden behind the Zone of Avoidance, contributing to the motion? It's like living in a deep valley surrounded by perpetual fog. You can feel the immense gravitational pull of a nearby mountain range, and you've mapped the foothills at the edge of the mist, but the true peaks, the highest summits, might still be concealed. Their full scale a mystery. This changes the Zone of Avoidance from a simple blind spot into the next great frontier of cosmic cartography. Every new survey that can see through dust and stars brings the potential for a monumental discovery. What other giants are waiting in the shadows, their gravity subtly steering the motion of galaxies we can see? The quest to complete the map of our local universe pushes us to look not just farther away, but through the obstacles right in front of us. And as our vision clears, we have to ask how we measure the true weight of these giants we find. Mapping the giants we know is one thing. Finding the ones we don't, that requires a new kind of eye on the sky. And that eye is almost ready. Up in the Chilean Andes, the Vera C, Rubin Observatory is set to start the most ambitious astronomical survey we've ever tried. For 10 years, its enormous camera will scan the entire southern sky every few nights. This isn't just a snapshot, it's a cosmic movie, a decade-long time lapse they're calling the Legacy Survey of Space and Time. LSST, it's going to see things that are fleeting, things that change, things so faint they've been invisible until now. Zeljko Ivzik, he's the project director. He talks about its purpose with this sense of anticipation. He says the most exciting discoveries will be the ones we can't even imagine yet, the unknown unknowns of cosmic structure. The numbers are staggering. The telescope's primary mirror is over 27 feet across. It gathers immense light, but the real marvel is the camera. A 3.2 gigapixel digital eye, the largest ever built for astronomy. Every image it takes would need over 1,500 high-definition TV screens to show it. Night after night for a decade, this instrument will build a catalog, over 20 billion galaxies, and a similar number of stars just in our own Milky Way. It will watch for anything that moves, flashes, explodes. This relentless gaze will turn our maps from static charts into something dynamic, a living atlas. The science it unlocks ties directly into the search for the largest structures. One of its main missions is to measure weak gravitational lensing. That's the subtle bending of light from distant galaxies as it passes through the invisible scaffolding of dark matter. By analyzing the slight distortions in the shapes of billions of galaxies, LSSD will chart the dark matter web in 3 dimensions. For the first time, we'll have a detailed mass map of the cosmic skeleton. Not just the luminous galaxies clinging to it. This could reveal dark matter filaments and halos on scales we don't see now, maybe pointing toward gravitational basins even larger than Laniakea. At the same time, the survey will find millions of supernovae. These stellar explosions are standard candles. They let us measure cosmic distances with incredible precision across vast stretches of space and time. This data puts the expansion history of the universe under a microscope, refining our measurements of dark energy, maybe resolving tensions like the Hubble constant debate. It'll tell us if the expansion rate has changed over time in ways our models don't predict, which could be influenced by the gravitational pull of unseen superstructures. Then there's the sheer census of galaxies. By plotting the positions and redshifts of tens of billions of galaxies, LSSD will make a 3-dimensional map of the visible universe. Hundreds of times larger than our best current surveys. In that ocean of data, algorithms will search for new patterns. They'll find galaxy clusters by the thousands. Trace faint filaments connecting superclusters, delineate the boundaries of voids with unprecedented clarity. It's almost certain to reveal new cosmic giants. Walls, complexes, voids that dwarf our current record holders, pushing the scale of homogeneity even further out. To grasp the leap, picture our current best maps of the cosmic web. They're like the hand-drawn portolan charts from medieval navigators, beautiful, insightful for their time, but filled with blank spaces labeled "Here There Be Dragons." The LSSD map will be like switching to a modern, high-resolution GPS that updates in real time. We'll see the continents and oceans of the cosmos with perfect clarity, and we'll watch how currents of matter flow between them over cosmic epochs. Beyond galaxies, this survey will do a complete inventory of our solar system, finding millions of new asteroids and icy bodies, mapping the frontier from Neptune outward, and it might even detect the faint imprint of primordial gravitational waves. Ripples from the universe's first violent moments, offering a direct glimpse into the mechanism that planted the seeds for all structure. So what happens when this new map is complete? It forces the next great redefinition. Our place among these giants gets recalculated. The philosophical implications are profound. Each time we build a better tool, the universe shows us we are smaller. And its architecture is grander than we dared to suppose. The Vera C, Rubin Observatory isn't just a telescope. It's a time machine and a cartographer's dream. About to hand us a new set of keys to a cosmos that is still wonderfully full of surprises. The vastness we've mapped, it does something to the mind. Astronauts have a name for that shift. They call it the overview effect. From orbit, looking down, they get this sudden, visceral understanding. Earth isn't an endless landscape of borders. It's a single, fragile, glowing blue marble hanging in absolute blackness. That perspective rewires you. Now take that feeling and expand it across billions of light years. That's the cosmic overview effect. We're not just on a pale blue dot, we're in an immeasurable web, a speck within a speck, within an ancient architecture of staggering scale. Confronting Laniakea, the great walls, the voids, it forces a profound humility. It's the ultimate redefinition of our place. Carl Sagan gave voice to this. He reflected that our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, he said there's no hint that help will come from elsewhere to save us from ourselves. Neil deGrasse Tyson often echoes this. He notes the universe is under no obligation to make sense to you. These aren't statements of despair, they're calibrations. They adjust our sense of significance. For most of human history, we placed ourselves at the center. The sun revolved around us. The stars were a decorative canopy. Each scientific revolution has been a dethronement. The Copernican principle moved us from the center of the solar system. Hubble showed we were not the only galaxy. Now cosmology reveals we're not even in an average place. We may dwell in a cosmic void, on a minor filament of a web so large we can barely comprehend it. This knowledge transforms our self-perception, our conflicts, our triumphs, our entire history. It all unfolds on a mote of dust, adrift in a supercluster we've only just learned to name. It shrills human concerns to a whisper, and yet, simultaneously, it connects us to the grandest possible narrative. We are made of atoms forged in stars. Stars that lived and died in galaxies, galaxies that are part of these immense structures. We are not just in the universe is in us. We are a way for the cosmos to know itself. That connection is more profound than centrality. You can see this layered reality in one iconic image, the Hubble Extreme Deep Field, a photograph of a patch of sky seemingly empty. Smaller than a grain of sand held at arm's length, in it thousands of galaxies. Each smudge of light is an island of billions of stars. Each galaxy is likely part of a group. Strung along a filament of dark matter, that filament is part of a wall which borders a void, which is one bubble in the cosmic sponge. Our entire world, every person who has ever lived, exists within a similar pinpoint. In someone else's deep field image, the scale is simultaneously crushing and exhilarating. So does this cosmic perspective isolate us, or does it connect us more deeply? It does both. It isolates our ego, our sense of self-importance, but it connects our substance, our origin story, to the entire unfolding drama of the universe. We are transient. These structures we see are transient too. On a timescale of billions of years, they're evolving, flowing, merging, and dissolving in the expanding cosmos. Which leads to a final, inevitable question. If these are the giants that shape the universe today, what becomes of them in the far future? What is the ultimate fate of an immeasurable heaven? The story of these cosmic giants doesn't stop with finding them. It keeps going across timescales that make human history seem tiny. It moves toward a future where the universe won't even remember their shapes. Our maps are just a snapshot, a single frame in a very long film. And how that film ends depends on the most mysterious thing we know, dark energy. What happens to Laniakea, to the Great Walls, to the whole cosmic web, comes down to what dark energy really is. This repulsive force that now runs the cosmos. We're living in a kind of golden age for cosmic structure, but it's a brief window. It won't last. Cosmology points to a long, quiet fade. A future often called the heat death. In that vision, the accelerated expansion from dark energy becomes everything. Over trillions of years, space itself keeps stretching faster. The first thing to go will be our view. Galaxies outside our immediate family, outside our local group. they'll start receding faster than light can catch up. Their light will stretch, redshift into nothing. They won't vanish all at once. They'll fade, like ships going over the horizon, their signals just getting fainter until there's only silence. Cosmologist Lawrence Krauss has a picture of this, a time maybe 100 billion years from now. Astronomers in our merged Milky Way and Andromeda galaxy will look out at a profoundly empty sky. The cosmic microwave background, the afterglow of the Big Bang, will have redshifted away, undetectable, all evidence of an expanding universe, of a violent beginning, of other galaxies. It will all be gone. Beyond a horizon you can't cross, the universe will look static, island-like, eternal. The great discovery of the 20th century, that we live in an expanding cosmos full of galaxies, that will become impossible to know. All records of the giants we mapped will be lost, and the structures themselves, their fate is tied to dark energy. If dark energy is constant, like the simplest models say, then the cosmic web will dissolve in slow motion. Gravity's pull, which built the filaments and walls, gets overwhelmed by the outward push of expanding space. Think of the web being stretched on a cosmic rack. The filaments connecting superclusters grow longer, thinner, more tenuous. The delicate bridges of galaxies between nodes stretch until the gravitational thread snaps. Superclusters like Laniakea, they're not gravitationally bound now. They'll never become bound. Instead, expansion will isolate their cores. The great attractor will lose its grip on the outlying filaments. What's left will be bound islands. Our local group, merged into one elliptical galaxy, will be one island. A few other massive, merged galaxy clusters will be others. Each surrounded by an ever-widening gulf of truly empty space. The voids will win. They'll merge and grow, consuming the thinning web, until each island universe is separated by an ocean of darkness, so vast no signal can ever cross it. You can picture a great metropolis at night, seen from a hilltop. First, the distant suburbs wink out, then the lights in the outer boroughs dim and go dark. District by district, the city shrinks into a smaller pool of light, until only the dense downtown core remains, a solitary beacon on a huge black plain. That's the fate of the luminous universe. The downtown cores are the final, bound galaxy clusters. Everything else fades into the abyss, so we began by learning to see the giants. Redefining our place inside an architecture of staggering scale, and we end by seeing that all architecture is temporary. These structures aren't eternal monuments. They're dynamic patterns in a cosmic flow, patterns that emerged, peaked in complexity now, in this era, and will one day dissipate. Their legacy isn't in permanence. It's in their existence as a chapter in the universe's story, a chapter we were lucky enough and curious enough to read. In a future with no external witnesses, the memory of these giants, the vast walls, the immense voids, will live only in the knowledge we gathered in this fleeting, luminous moment. And that makes mapping them not just science, it's a form of cosmic remembrance. Each of these giants forced a different kind of redefinition. Laniakea redefined our address. Home isn't a cluster, it's a flowing continent. The cosmic web redefined connection. It showed a single living anatomy for the entire universe. The Boötes Void redefined emptiness. It proved nothingness has shape and scale. It dominates the cosmic landscape. The end of greatness redefined our theories. It made us question if smoothness is a promise or a limit we haven't yet reached. The Great Attractor redefined hidden influence. It's a reminder that the most powerful forces are often the ones we cannot see, and the dark, expansive future redefined permanence itself. It framed these colossal structures as fleeting patterns in an infinite flow. So the true story these 25 structures tell, is it one of deeper order or profound chaos? The answer seems to be both. we find an order, a beautiful filamentary web governed by gravity and dark matter, following mathematical rules we can decipher. Yet within that order we find chaos, wildly improbable giants, voids of staggering scale, and a future that erases all trace of this intricate architecture. The universe is not a bland, smooth soup. It is a dynamic, textured, and evolving masterpiece, with room for both elegant design and spectacular, rule-bending anomalies. Ultimately, this list is not a catalogue of objects. It is a history of scientific revolution. Each entry marks a moment when our tools, our courage to look deeper, forced our understanding to grow. Every time we built a better map, the universe presented a new layer of complexity. It humbled our previous certainty, this journey from the local group to the edge of the observable horizon. It's a story of human curiosity, persistently confronting a reality grander than its assumptions. These 25 structures are monuments to that process. They stand as waypoints in our ongoing effort to answer the oldest questions, proving that the cosmos is always ready to redefine itself, and in doing so, redefine us. Our trip through these giants doesn't end with an answer. It ends with a different way of seeing. We went from our local supercluster all the way out to the observable edge. And what was there wasn't chaos, it was structure, a kind of architecture, filaments and voids, a tapestry woven on a scale that's hard to even hold in your mind. The universe isn't just stars scattered at random. It's a cosmic web, and we're inside it, we're threads in it. Each of these 25 massive things taught us something. Laniakea showed us our real address. The Great Walls showed us the sheer scale of texture in the cosmos. The voids showed us that emptiness has a shape, it has a name. And then something like Hyperion, that distant proto-supercluster, showed us these giants are born in the earliest dawn. Every one of these discoveries made us let go of a smaller, simpler idea. We had to accept a reality that's much bigger, more complex. That's the theme, really, redefinition. Our view of the universe isn't a fixed picture, it's a living map. And it's constantly being redrawn by curiosity, by better tools. These largest structures are the milestones. They mark when we looked deeper, when we built a new instrument. When we had the courage to burn the old map so a new one could appear. Edwin Hubble, his work started this whole shift in perspective. He talked about this. He said, equipped with his 5 senses, man explores the universe and calls that adventure science. That's the adventure we've been on, using our senses, extended by telescopes and computers, to listen to the story the cosmos is telling. So next time you're under the night sky, try to see it differently. Don't just see points of light. See the faint traces of an immense filament. See the dark spaces not as gaps but as voids. The dominant feature of a cosmic sponge. You're looking at the architecture of everything, and you're inside it. We'd like to hear which structure changed your view the most. Was it Laniakea, that flowing continent, or the staggering nothingness of the Boötes Void? Share that in the comments. This conversation is part of the adventure, too. If journeys to the edge of understanding call to you, subscribe, and always remember to look up. You're not just an observer of this story, you're made from the stars in these galaxies. You're shaped by the same forces that built these walls, and your curiosity is the tool that maps them. You are part of this grand, unfolding tapestry. The adventure continues.